The poets and songwriters have always characterized the heavens as unchanging. The stars are immortal, in contrast with the ordinary life processes on Earth. Daylilies and butterflies may be fleeting, but the sun and stars will endure. However, even the stars go through definite life cycles, and their story is a fascinating one. After all, every single atom of calcium in every bone in our bodies was produced inside an ancient star, which then exploded and added the processed material to the interstellar medium, some of which later went into forming our sun, Earth, and solar system, and finally, us. Astronomically, in human terms, the story begins a mere 75 years ago. Scientists at that time had no real understanding of the energy sources that allow the stars to shine. All the known possibilities, from chemical reactions like burning wood in a fire, to utilizing gravitational potential energy stored in the star, in other words, having the star contract to smaller and smaller sizes as it radiated, fell woefully short of the required energy. All these energy sources could power the stars for a mere 1,000 to possibly 10 million years. However, our knowledge of the age of the rocks and the Earth indicated several billion years of existence for the sun. A crisis inevitably ensued. Hans Bethe, working at Cornell, showed that nuclear physics provided the missing link in the chain of knowledge which now describes the structure and evolution of the stars. So many observational puzzles have been explained once the hypothesis of nuclear burning was adopted that there can be scarcely any doubt that these enormous balls of fiery gas are powered by insignificant subatomic particles so small that it would take about 1 trillion of them lined up end to end to span the head of a pin. The universe is indeed a miraculous place. The immense energies provided by the nuclear furnaces in the cores of stars are the result of one-way transmutations of elements, beginning with hydrogen to helium. It is these processes which cause the stars to evolve. As the star cooks the elements from hydrogen to helium to carbon and oxygen, there is progressively less and less energy available to extract. Once the core of the star reaches iron, the jig is up. No longer can the star replenish its expenditure of radiation, and it must change its structure radically. Depending on its mass, it can either cool down gradually, eventually dying like an ember in a fire, or go out in a blaze of glory with an utterly catastrophic explosion, becoming a supernova. During this explosion, which lasts only minutes, the released energy is so great that for a short while, the star outshines the entire galaxy of which it is part. Imagine an object shining brighter than the sun by 100 billion times. Although the actual explosion lasts for less than a day, the effects linger for centuries. The gas from the explosion hurtles outward at speeds approaching that of light, and it begins to plow through the space between the stars. We can see the accumulation of material, called a supernova remnant, still expanding today, even when the original explosion occurred thousands of years ago. Here, you see a remarkable double-exposed photograph of the Crab Nebula, which was first visible in the skies of 1054 AD. One image was printed as white, the other, taken 14 years later, was printed and superimposed black. You can almost feel the seething cauldron as it hurtles through interstellar space. Here you see a composite photo of the same object using a Chandra X-ray observation, shown in blue, a Hubble optical observation, shown in green, and a Spitzer infrared observation, shown in red. The engine that powers these nebulae are often quite active too. Here we see a video of X-rays from Chandra shown in blue and optical photons from Hubble shown in red of the central part of the nebula. This remarkable sequence was taken like a slow-motion video over a period of about 6 months in 2000 and 2001. And don't forget, all this started becoming visible almost 1,000 years ago. Often the explosion leaves behind a strange object. The very center of the region does not disperse, but forms a neutron star. We met this kind of object last week in a different context when we examined Cenex 3. This is a star that has more mass than the Sun, but occupies a volume no bigger than the city of Boston. Its density is truly astounding. One thimbleful of its material would weigh as much as millions of full-sized African elephants. It usually spins on its axis 10 to 100 times a second and is called a pulsar, even though it doesn't pulse at all, but as we have seen, rotates instead. As the pulsar spins over the centuries, it adds electrons and other charged particles to the interstellar soup and provides the energy we see radiating towards us today from parts of the remnant. Since such high energies and temperatures are involved, it is not surprising that these supernova remnants can radiate copious amounts of X-rays. The pictures we get from these objects tell us many things. Not only do we get an idea about the star that exploded, we also find out much about the interstellar medium itself as the star's energy sweeps up and accelerates the once calm environment surrounding the star. The more detailed the picture we get from these objects, the better our understanding. So we try to get data from all parts of the electromagnetic spectrum, including X-rays. As we have seen, the problem is that X-rays are hard to focus. But about 20 years ago, we learned how to use grazing incident mirrors for this purpose. The results were astonishing, and the improvements kept coming until now we have the superb optics of the Chandra satellite. We have looked at the Cas-A image before in DS9 several times. Now we want to explore some of the physics that give rise to this incredible picture. Here we see the display of our image set to emphasize the following discussion. I urge you to play around with DS9 using OBS ID 114, which is the first data set listed when you initialize the virtual observatory. First, you see portions of a rotated square, which shows you the extent of the Chandra satellite's field of view. Also, you see a very bright, almost white, lumpy but somewhat circular region surrounding a central point-like object. Outside the lumpy region, we see a fainter, more wispy region. What is all this telling us? We have pieced together the following story. About 300 years ago, the star that is now the central object exploded. Remarkably, this conflagration was not seen by anyone apparently, even though these explosions, as we have seen, are usually large enough so the radiation can provide enough light for reading even at midnight. How then do we know when it happened? Optical data shows material via the Doppler effect streaming outward from the object at thousands of kilometers per second. If we run this expansion backwards, the material would get back to the center in about 350 years. Thus, the object should have been visible around 1650 AD. Since this remnant has been expanding for over 300 years at incredibly high speed, by now it is quite large. As is usual with astronomical objects, Distances to supernova remnants are very difficult to determine. The best estimates come from the fast-moving knots of material that we can actually see moving outward through the sky over a period of years. We have just seen an example of this in the Crab Nebula. In the case of Cas A, the bright spots you see in the X-ray image are examples of some of these knots. If we know how fast the knots are moving through space, Doppler shift again, and we know how far they move in angular extent across the sky, we can compute the distance to them. In your assignment this week, you will be exploring this idea in depth. The bright, almost circular ring that we see in this image of Cas A is the current position of the shocked debris from the explosion. In reality, is a large hollow shell with very little material in the interior region near the pulsar, since the explosion has swept up the material much like a snowplow does when it drives through snow. Because the material is moving so rapidly, a shock wave forms. We see this as a faint outer shell outside the main ring of ejecta. The jet-like structure, visible on the left side of the remnant, may indicate higher velocity material rushing outward through a rarefied part of the interstellar medium. If you look carefully at the shape of this jet, you can see that when you follow it back towards the center of the remnant, it seems to be aligned with that faint little dot, the central object in the very middle. From your homework results this week, you will see that the intensity of the remnant steadily increases from the center until about 100 arc seconds in radius. Thereafter, the remnant gets weaker and weaker. This is what you might expect for a more or less hollow ball with a dense outer shell. In fact, the exact nature of this emission and its morphology or shape is a subject of intense research currently. By looking at profiles like these, astronomers hope to gain some insight into the nature of the original explosion and better understand the mechanisms by which the shock fronts form and travel through space. The best, however, is yet to come. Some of the most exciting data from this object concerns the energy spectrum of the X-ray light from different parts of the remnants. Just as blue flame is hotter than a red flame, and sodium vapor lights are yellow while mercury lights are blue, X-rays can tell us about the state of emitting regions and what substances are present in each part of the object. And when you look at the energy of all of the X-ray photons that Chandra can collect from Cas A, a remarkable picture emerges. Superimposed on a continuous background of X-ray light, we detect the fingerprints of the elements. Like that prism that takes sunlight and makes a rainbow out of what we think is only yellow light from the sun, so the detectors on Chandra examine X-rays. And just as that rainbow contains information about the chemical composition of the sun, so the Chandra energy spectrum tells us about the recycled material from our supernova. It's all there, the building blocks of life: calcium, oxygen, iron. Let's go to DS9 and check this out.